In this next module, I'm going to give you more details about sample size calculations, and I'm also going to derive for you a sample size formula. First of all, in order to be able to follow this module, you need to know the distribution of a difference in means and the distribution of a difference in proportions. In week 5 of the course, I told you about the distribution of a single mean. The distribution of a difference in means is very similar. It follows a t-distribution. The mean is the true difference in means. The standard error for the difference in means is the square root of the variance of the characteristic you're looking at divided by the sample size of group 1 plus the variance of the characteristic you're looking at divided by the sample size for group 2. Notice that looks very similar to the standard error of a single mean, but we have variability coming from two groups. We're comparing two groups here. So we have variability from two means, from two sources, and that's why there's a sum there under the square root. The distribution of a difference in proportions, like a single proportion, follows a z-distribution. The mean is the true difference in proportions. The standard error for a difference in proportions, again, looks very similar to the standard error for a single proportion, but because we have two groups, we get variability coming from both of those groups. So n represents the sample size from one group, m represents the sample size from the second group. What is power? Power is the probability that at the end of the day, after you do your study, you're going to correctly reject the null hypothesis when you should, when in fact the null hypothesis is false and there really is an effect out there. Another way to say that is it's the probability that you're going to find a statistically significant result when you do your study. Keep that in mind. We're aiming here to get a statistically significant result if we should. That's what power is about. So let me set up the logic now of sample size formulas. The goal of the sample size formula is to say how big of a sample do I need in order to have a certain statistical power, or another way to say that is how much power will I have for a given sample size. Let me show you some examples that kind of walk you through that logic, and then we'll get into the more specific mathematical details. So take an example here. Imagine I've got a study where my statistic that I'm looking at is the difference in proportion. So I've got two groups. I'm looking at the proportion that, say, have depression or whatever the outcome variable might be. And what I'm showing you here are two distributions. There's a null distribution. Whether or not we get a statistically significant p-value depends completely on the null distribution. Remember, our hypothesis test will compare the result in our experiment to the null distribution. So the null distribution, notice, centers around a difference in proportions of 0, because our null hypothesis here is that the difference in the two groups is 0. There's a certain shape to this distribution. It's a normal. Difference in proportions follows a normal distribution. And the width of this curve is just related to the standard error. That's the null distribution. So that's the top graph you're looking at. What are you looking at the bottom? At the bottom graph, you're looking at the alternative hypothesis. So when you do a sample size calculation, you have to state what you think the actual difference is in the real world. And that's usually not the null difference. You usually think there is really an effect. So you have to state what you think the real effect is. So if we think that there's a real effect out there and it's a 10% difference, so we have to state what that is. I'm saying for some reason we believe it's a 10% difference. That's our alternative hypothesis here. If there's really a 10% difference out there in the real world, then what this second graph, the second distribution on the bottom here represents is what we would expect to see in our study if the true difference is actually 10% rather than 0%. So if we believe the true difference is 10%, here's the various differences in proportions that we expect to see in our study. We might see a 2% difference all the way up to an 18% difference if the true difference is 10%. How do we decide whether or not we're going to end up with a statistically significant p-value? Well, in order to get a significant p-value, we have to be in the tail of the null distribution. We have to be above a certain value based on the null distribution. That value is about 2 standard errors above 0. In this particular example, let's say the standard error is 3.3%. If we multiply 3.3% times 1.96, about 2, we see that in order to get a significant p-value here at the 0.05 level, we are going to need to see a difference between the two groups in our study of at least 6.5%. So that's based on the null distribution. Well, if that's our critical value, that's the level we need to be at, see in our study in order to get a significant p-value, Now let's turn to what we think the real world looks like, what we think will actually happen in our study if the true difference is 10%. Let's scroll down to the alternative curve here. If there really is a difference of 10% out there, then how often are we going to actually see in our study a difference of 6.5%? That's the area to the right of the critical value on this curve. That's the power. That's the power, that's the chance that we are going to reject the null hypothesis here as we should. So if the true difference is 10%, we're going to be above 6.5% about 85% of the time. That's that yellow area there. And we can calculate that specifically because remember, we know we're on a z-curve, on a standard normal here, so it's very easy to calculate probabilities here. So again, what's the chance? If the true difference is 10%, what's the chance we're going to see in our study at least a difference of just 6.5%? Well, we can directly calculate that from the z-curve. So the mean of our alternative curve is 10. We need to get to the critical value of 6.5. How many, if we're on a standard normal curve, where are we? So here's my standard normal curve with a mean of 10. I need to be above 6.5. My standard error of this curve here is 3.3. So what's this area? How would I calculate this area? I want the area to the right of 6.5. So we can translate the 6.5 into a z-score. It's a z-score of negative 1.06. The area to the right of negative 1.06 on a standard normal curve is 85%. So that's the thought process that goes behind calculating power. Let me just give you another example. So what if, in that first example I showed you, the sample size was about 1,500. What if we had a much, much smaller sample size? Same null hypothesis, same real effect in the world. So the null hypothesis is still a difference of 0%. Let's say that there really is a difference. The true difference is a 10% difference. But let's say we were doing a much smaller study. What happens if we do a much smaller study? Our standard error is much, much bigger. The variability of our statistic is much, much larger. Now, in order to be able to reject the null hypothesis, to be in the tail of the null distribution, our critical value now comes out to be a 20% difference. Since our standard error has now gone up to 10%, we have to be past a 20% difference in order to reject the null hypothesis here. Well, if the true difference in the real world is only a 10% difference, we're not going to see 20% differences that often. We're only going to see 20% differences about 15% of the time. The area to the right of 20% on my alternative curve here is now only about 15%. So you can see that smaller sample sizes are directly going to reduce statistical power. Let me give you an example now that's a difference in means rather than a difference in proportions. It basically works in the same way. Imagine we've got a situation, again, our null hypothesis that the difference in the means between the two groups, the example here is using IQ scores, so if there's a 0-point difference in IQ scores, that's our null hypothesis. Let's say that we believe in the real world that the true difference is actually a 4-point difference in IQ points. Based on the standard deviation of IQ score and the sample size here, you can see that the null curve and the alternative curve don't really overlap at all. In order to be able to reject the null hypothesis here, we just need to be, in our experiment, have a difference between the groups of more than 1 IQ point. Well, clearly, if the true difference in the real world is a 4-point difference, we're almost guaranteed to see at least a 1-point difference in our study. So the power is nearly 100% in this scenario. But what if I take that IQ test and I make it have greater variability? So the standard deviation for this IQ test was greater. What's that going to do to the scenario? Of course, that's going to increase the standard error here. That's going to make this curve wider. Now, in order to reject the null hypothesis, we're going to have to see a difference in IQ scores between the two groups of at least 5. How often does a difference of 5 occur if the true difference is a 4-point difference? Well, it's about a 40%. If you look at the area to the right of that red line now, it's at about 40%. So more variability in the outcome is going to reduce our statistical power. What if the real effect in the real world was smaller? What if the true effect was only a 1-point difference between the groups? If that's the case, then it's going to be harder to detect that difference. Since the critical value is 1 and the true value is 1, then there's about a 50% chance that we're going to find a statistically significant difference for that scenario. So smaller effect sizes will also reduce our statistical power. So you can see that all of these factors work together to affect statistical power. If we have a bigger effect size, that's going to increase our statistical power. If the thing that we're measuring, our outcome, is more variable, if the standard deviation is greater, that's going to decrease our statistical power. Bigger sample size will increase our statistical power. If we want to have a more stringent significance level, all the scenarios I've shown you up till now, I've been talking about a significance level of 5%. In order to reject the null hypothesis, we needed the p-value to come out lower than 5%. But what if for some reason we wanted to make that more stringent? We only wanted to reject the null hypothesis if the p-value was less than 1%, 0.01 for example, maybe to correct for multiple comparisons. If we change that significance level, make that more stringent, that's going to decrease our statistical power. And I can illustrate all of these, again, using these two curves. So here's the null curve and the clinically relevant alternative curve. If I increase the effect size, if the true difference in means is even bigger, that's going to pull those two curves apart. That's going to increase my statistical power. If I increase the standard deviation of the characteristic that I'm looking at, that's going to increase standard error, that's going to increase the width of those curves, that's going to make them overlap more, that's going to decrease my statistical power. If I increase the sample size, that's going to shrink my standard error, that's going to shrink the width of those curves, that's going to make them less overlapping, it's going to increase my statistical power. If I shift my significance level, if I want my significance level to be smaller than 5%, more stringent, that's going to pull my rejection region to the right. It's going to make those two curves overlap more, and so that's going to decrease my statistical power. So based on these elements, you can write out a formal mathematical equation that relates all of those elements: power, sample size, effect size, standard deviation, and significance level. And then if you want to solve for the sample size that you need for a given power, you're just going to solve for sample size. And we're going to derive those formulas, one of these formulas, shortly. But let me just show you the end product of one of these derivations. So here is a standard formula for calculating the necessary sample size for a given power if the statistic that you're going to be looking at the end of the day is a difference in means. You can see that all the elements I just talked about are in here. So if we want to calculate how many people do I need in each group for a given power, well, if the standard deviation of the outcome variable, if that variability is higher, I'm going to need a greater n, a greater sample size for the same power. So that standard deviation is in the numerator. If I want to increase my power, say not look at 80% power, but look at 90% power, of course that's going to increase my sample size needs. If I want to make my significance level more stringent, that's also in the numerator, that's going to increase my sample size needs. However, if the effect size increases, if the difference in means is bigger, that's going to decrease my sample size needs, so that's in the denominator. The difference in proportions formula is almost identical. I'll just point it out here. Sample size, again, is related to more power. It's going to require more sample size. More stringent significance level is going to require more sample size. For proportions, the measure of variability, remember, is p times 1 minus p, so that's also in the numerator. And the effect size, the difference in proportions, is in the denominator. So exact same relationships. Now I want to walk you through the derivation of one of these formulas, of the difference in means formula. So let's start with just a particular example, and then we'll generalize from there. So here's a situation where we're looking for a difference in means, that's our statistic, and the standard error here is about 0.5. The critical value then for 5% significance is around 1. And let's say the true effect in the real world is an effect size of 1. So we have about 50% power here. Well, where did I get that 50% power? Where did that come from, other than just visualizing it here? I'm going to generalize things a little bit now. So rather than saying the critical value is 1, let me say where did that come from. So the critical value for a difference in means, the null value is 0. And then we're going to be adding to that in order to be in the top 2.5% or whatever percentage, and to be in the tail of the null distribution. I'm going to be adding to that 0 the standard error, in this case the standard error of a difference in means, times the significance level, the z that is associated with the significance level. Now z alpha over 2 is usually 1.96, but if you wanted to change the significance level to make it more stringent, you would change that z value. So that's why I'm generalizing that here. The power is then going to be the area to the right of what I'm going to call z beta. So z beta, remember this alternative curve down at the bottom is just a normal curve. And we want to know what's the power on the alternative curve, what's the area to the right of the critical value? The critical value we figured out based on the null distribution. What's the area to the right of the critical value on the alternative curve? To figure out that, we're going to have to calculate a z-score based on the alternative curve. The z-score will take the critical value, we want to know where we are on this curve, that's the critical value, minus the mean of the alternative curve, which is just the alternative difference here is an effect size of 1. And then we divide that by the width of this curve, which is just also the same standard error, the standard error of the difference in means here. Let me just plug in some numbers to show you here. So here, z beta, what I'm calling z beta, remember the critical value is 1, the true effect is 1, so that subtracts to a difference of 0, divided by the standard error of the difference. And that turns out to be a power here of 50%, because a z value of 0 obviously is associated with an area of 50%. So let's just generalize this now. So the power in this scenario is going to be the area to the right of z beta. And again, what am I meaning here by z beta? So when we're on the alternative curve, here's the effect size, what I'm calling the alternative difference. That's the mean of the alternative curve. The width here is the standard error, in this case the standard error of a difference in means. The critical value is what came out of the null curve, and that might end up anywhere on this curve, but wherever it ends up, I'm going to call that z beta. How do I calculate z beta? How do I determine what this is the critical value, and I want to translate it into a z-score? How do I make a z-score? Well, I take the critical value, whatever that value is in the original units, I subtract the alternative difference, that's the mean of that curve, and I divide by the standard error of the difference, that's the standard deviation, the width of that curve. That's the general formula I've written up here. So that's a general formula for power. If I then take that z beta and I go to a standard normal chart and I find the area to the right, that will be my statistical power. So that's the idea here. Now we can go a little further, however, because I can just do a little bit of math here. Remember, what is the critical value? The critical value is z alpha over 2 times the standard error. That's what we got out of the null curve. That's the critical value. We need to exceed that in order to reject the null hypothesis here. So I can just plug that in where I've written critical value. I'm subtracting from that the alternative difference, and I'm dividing by the standard error of the difference. These two standard errors in the numerator and the denominator are the same, so I can cancel them out. I end up with that z beta is equal to the significance level, z alpha over 2, minus the alternative difference in means, the real difference in the real world, divided by the standard error. Now I'm going to make a little trick here. I am going to remind you that when you go to a z standard normal curve, a chart, the way these charts are set up, they always give you the area to the left of z. In this case, we want the area to the right of z. One way to get the area to the right of z is just to multiply whatever z you have by a negative. If I look to the area to the left of z is the same as the area to the right of negative z, and vice versa. So a little trick that you can do here is just multiply this whole equation by a negative. I'm going to do that, and I'm going to name this new quantity z power. All that does for you is now, instead of going to the standard normal chart and having to figure out the area to the right, you can take z power to the standard normal chart and figure out the area to the left, and that will represent the power. So it's just a little trick to save you time. So when I'm calling z power, now you can take directly to a standard normal chart. The area to the left of z power is the same as the area to the right of z beta. That's the whole idea. So now we have here a general all-purpose power formula. If you want to calculate z power, and then you can go take that z power and find the area that goes with it to the left, you take the alternative difference, that is the true difference in means, you divide it by the standard error of that difference, and you subtract the significance level that you want. It's very simple. But now we can go one step further, and we can plug in the standard error of the difference in means. Because remember, we're trying to get sample size out of this, and I don't see sample size in this formula yet. Where's the sample size? It's buried in that standard error. So remember, the standard error of the difference in means I showed you earlier is the variance of the characteristic you're looking at divided by the sample size of one group plus the variance divided by the sample size of the other group. It's a square root of that. So now we can plug that in for the standard error of the difference. The other thing I'm going to do here is I'm going to allow that the sample sizes in the two groups could be different. They don't have to be the same. But I want to solve for a single n. I don't have to solve for two different n's. So what I'm going to do is I'm going to call n1 the size of the smallest group. And then I'm going to add in a new term here, r, which is the ratio of the larger group to the smaller group. If I want one of the groups to be larger, I can represent that group as r, the ratio of the larger to the smaller, times the smaller group. That allows me to allow the sample sizes to be different in the different groups. Okay, using all of that, we can now plug into our all-purpose power formula. I'm plugging in the standard error of the difference, and again, the sample size is represented as n and r times n. And then from here, it's just algebra. So notice that I'm going to rewrite the material that's under the standard error just to add those up, give them the same denominator, r over n1. Now I've got a square root in the denominator. I want to get rid of the square root. So I'm going to add z alpha over 2 to both sides of this equation. Then I'm going to square everything so that I can get rid of the square root. Then I'm going to cross multiply. And what I end up with when I cross multiply is this quantity that you see in the first line here. And then I'm just going to do a little bit of algebraic rearrangement. Remember, I'm trying to solve. I'm trying to isolate n. So I'm just going to do some algebra to isolate n here. And I come up with this formula here. And we can rewrite this to be a little bit neater to be this formula here. This is my formula for a standard error. This is my sample size formula for a difference in means. And again, R allows us to have, this is the N1 is the size of the smaller group. The size of the bigger group will be R times N1 if we have an unequal sample sizes. But this is basically the formula that I showed you at the beginning. I didn't show you at the very beginning the R plus 1 over R. I just put in the 2, assuming equal groups. We can even generalize a little bit more to allow unequal groups. So that's the formula for sample size for a difference in means. Now we've derived it. Problem. Let's say that you're wanting to compare two groups, a group of male doctors and a group of female doctors, and you want to have enough power to detect a 3-point difference in IQ between the two groups. And if you expect a standard deviation of IQ score to be about 10 on an IQ test for both groups, how many people would you need, assuming that you're going to have equal sized groups, to achieve a power of 80%? And a power of 80% corresponds to a z power of 0.84, because if you're on a standard normal curve, the area to the left of 0.84 is about 80%. I can just take those numbers and plug into the formula here. So 2 times 10 squared is 100, z beta is 0.84, 1.96, that's corresponding to a 5% significance level. I want to see a difference of 3 points. So just plug into the formula. It tells me that I'm going to need 174 people in each group, so 348 altogether, because that's the size for one group, and I'm going to have two groups here. The general sample size when you're looking at a binary outcome, when you're comparing proportions rather than comparing means, is almost identical to the one for comparing means. I'm not going to derive that one separately because the logic is just the same. I'll challenge you to go and derive that on your own if you'd like. You would use this formula in much the same way. The only real difference is that the variability for proportions is p times 1 minus p as opposed to sigma, as opposed to the standard deviation of the trait you're looking at. Otherwise, they're exactly the same. The logic of the derivation is exactly the same.